Today I'm going to talk about our approach to neuromorphic sequence learning on a memristive array. And let's first start with why this is important, because sequence learning is considered one of the major core capabilities of the human brain, and we need it for basically everything like, do I have a pointer? Okay, then I use the mouse. Yeah, it's basically one of the core capabilities that we need for everything like movement, speaking, perceiving our environment, but also for high-level tasks like math, calculus, and reasoning. And when we talk about sequence learning or sequence prediction, more precisely, what we have is that we have a bunch of input streams, like here, these abstract characters ABD, ADBE, and FDBC. And when we see these sequences for the first time, then we cannot really know, seeing one character, we don't know which character comes next. But if we look at these sequences a couple of times, after some time, we know after A comes D, after D comes B, and so on. And with this, we can not only predict the next sequence elements, we can also generate mismatch signals if we see a sequence that we haven't seen before. And the special thing about sequence prediction in this case is that we have to learn a sense of context. Thank you so much. We have to learn a sense of context because you can see here in the middle we have DB, DB, and always depending on the first character, there's a different final character, and we have to maintain this sense of context to be correctly able to predict these sequences. Yeah, and we want to do this because we want to give this ability to hardware systems. Therefore, we design a neuromorphic hardware to get energy efficiency, small silicon footprint, and biological time constants. To do so, a colleague of mine took the very famous hierarchical temporal memory algorithm, or at least the temporal part of it, and implemented it with spiking neurons and biological synapses. And he coined this the spiking temporal memory. And this algorithm is so simple that we thought, okay, why not try to realize it on a real hardware system? So we took this spiking temporal memory and adapted the algorithm to make it fit to a dedicated neuromorphic hardware, which is based on a memristive crossbar array. And this is our mem spiking TM algorithm. The simulations parts was accepted just last week, I guess. And today I'm going to show you that it actually can run on hardware. Okay, let's first start with the system. You can see the system right here. We have a bunch of neurons, both excitatory neurons here and inhibitory neurons. And these neurons are ordered in so-called subpopulations, these boxes here. And each subpopulation stands for one abstract sequence character and receives external stimulus exactly for this particular character. At the heart of our system, we here have the memristive crossbar array that also Melika talked about, or similar to what Melika showed us yesterday. It's realized in the same technology on a 32 kilobit 1T1R array. And yeah, so the neurons together with our memristive array realize a Hebbian learning rule with inhibition and homeostasis. And the critical thing is you can see that all the inputs and outputs to our array are controlled solely by the neurons. So we don't need any dedicated memory controller to realize the algorithm. So what can we do in terms of compute and memory with a memristive crossbar array? One thing, of course, is we can do vector matrix multiplication, meaning we open all the transistor gates. We apply a vector here, an input vector. And that means that these red-colored devices will receive a read pulse or read signal and generate a current upon that. And this gives us basically the vector matrix multiplication of the conductances and the input voltage. But we can also do update in compute and memory. And to that purpose, we open selectively transistor gates, which are here vertically connected. That's the green box. And we, at the same time, apply a update pulse vertically. And exactly here at the intersection of open transistor gates and applied input pulse, we get updates in our devices. I don't have enough time to go over the complete algorithm, but what happens basically is that we have a clocked signal to our algorithm with read and update phases. And what happens in each read phase is that we stimulate one external character or more. And depending on which character we stimulate, these neurons will generate a spike. And spiking in our case means it will send a read pulse, which you can see here is colored in red. And as I showed before, it will generate an output current. Then in the update phase, what happens is that currently spiking neurons, so if we are in this time step here, currently spiking neurons are the neurons in B, will open their transistor gates, and the previously spiking neurons, so in this case, all neurons belonging to A, will send an update pulse, leading to a strong increase of the conductance exactly here at the intersection of both signals. So when we look at this very small toy example of the sequence ABC, we have the situation that, we apply ABC, or we stimulate ABC and read out these synapses. Reading out, in this case, also means that we depress the conductance of the devices a little bit. And when we when we look at the total change of conductance that is executed here, we see that all of the synapses in the system get depressed a little bit, except for those synapses leading from A to B and from B to C. And that are exactly the connections that we want to train for this toy sequence ABC. When we do this a couple of times, at some point the synapses will have increased their conductance sufficiently that the read pulse that we apply will generate a very high current, and this will predict the next neuron. So a read pulse will predict a next sequence element. And if sufficiently neurons in a subpopulation go in a predictive state, this hinders all other neurons in the same subpopulation from spiking. And this then leads to very sparse spiking activity in the system. Okay, so as I said, so far we only did this in simulation, but we can also now show that we can execute this algorithm in hardware. And to do so, we looked at this more complex example of the sequences ABC, then 2 pauses, and then DBA, and again 2 pauses. And as you can see, this is one of those more complex sequences where we have a common central character. So the system has to learn a context of B to be able to correctly predict the final sequence element. So when we stimulate this first subsequence ABC, you can see here the red triangles are the external stimuli. In the beginning, always the complete subpopulation spike. And the color coding in the background gives you the output currents that the neurons receive upon these spikes. And as you can see, in the beginning, it's very low. In this range, especially, it's below the so-called prediction threshold. And when we don't apply signals, it's no current at all. So now when we apply the second subsequence DBA, you also see that an external stimulus will cause the whole subpopulation to spike. But here we already have some predictions. That's these blue bars. However, they are wrong. So B predicts, in this case, B predicts a neuron in C, which is obviously wrong because after B, in this case, comes A. When we just show these sequences again to the network, what we see here is that A already correctly predicts a neuron in B. And here, a neuron or the spiking of D predicts a neuron in B. So that's already correct, but there are still some predictions missing. In the third epoch, the first subsequence is already correctly predicted. We have A predicting B, predicting C. The second one is still incorrect. And after 4 epochs, we have already correctly trained the sequence. A predicts B, predicts C, D predicts B, predicts A. And that's exactly what we wanted to learn. And if you look carefully, this is here the reason where we have this context sensitivity, because a different neuron in B is predicted depending on the first character. In simulation, we can also make this task more complex. We also solved the counter task that also Melika presented yesterday successfully with a relatively small network. And we can also, in this paper by Lazar, there was also a occluded task proposed, and we could also show that we can solve this more complex task with our algorithm. And to wrap up, the initial idea of using memristive hardware in a neuromorphic system is to gain energy efficiency. And here in blue, you can see the energy consumption per epoch during the training in the simulation case. And as you can see, we have an intrinsic decrease of energy consumption during the training. We start here at 500 nanojoules and end up at 300 per epoch. And this is exactly where the spiking becomes sparse. We also compared this to a floating gate implementation of the algorithm and could show that, we save 66% of energy at least. And this also holds for more complex sequences. Yeah, finally, I showed you a very small glimpse of our mem-spiking TM algorithm. We executed this successfully on a real fabricated 1T1R memristive array. And at least in simulation, we could see that we actually save energy. And with that, thank you for your attention.